All right. Hey, everyone. Welcome to CMU. My name is Virginia Smith, and I'm an assistant professor in the machine learning department. And if you're in Pittsburgh right now, you know the weather is really terrible. So I'm hopeful that my power will stay on long enough so they don't get kicked off here. So today I'm going to be talking about a portion of my research, which is in large-scale machine learning. And I'll also, at the end, talk kind of more broadly about other directions my group is pursuing. And I'm looking to take both PhD students and master's students this year. So kind of a high-level motivation for a lot of my work is basically to take machine learning out of its sandbox. And specifically what I mean by that is getting machine learning to scale to massive data sets and modern systems, and also ensuring that the models that we learn will perform well when we're done with this training process so that they can work well in the real world on real complex data sets. And I'm going to talk a little bit about both of these challenges today. One area where you see both of these things happening simultaneously is the problem of federated learning. So federated learning basically describes the following scenario where you want to perform training. You want to train a machine learning model across a network of distributed devices. So this, for example, might be a network of cell phones or wearable devices, or even organizations like hospitals. And the idea is that you want to train over this data while also not sending the raw data itself back to the central server. So you need to perform this training in a distributed fashion. And there are a lot of challenges to this setting that really differ from prior work in distributed learning. So one issue is that communication in these networks can be really, really expensive. So you can have massive networks, say, of millions of cell phones, and the networks themselves can be very slow. There may also be significant privacy concerns with sending the data. So for example, imagine that you're trying to learn some model over text message data or pictures from cell phones. That data could be very private, and you want to ensure that you're not leaking any of that information as you're performing this training process. And finally, one way that this setup really differs from prior work, say, in data center computing, is because the data is being generated on these remote devices, and you don't have the ability to sort of repartition all of that data. The data can be really unbalanced, and it can really be non-identically distributed across the network. So you might have some devices, for example, that generate data that looks very different than the data on other devices. This heterogeneity shows up not only in terms of the data, but also in terms of the hardware itself. So you could also have, for example, someone who has a new cell phone that has great connectivity, or someone who has a very old cell phone with poor connectivity. And these idiosyncrasies in practice can make this computing substrate really different than, say, a data center setting where you have much more reliable compute. So these are all problems that students in my group are looking at. I think they're all sort of equally important in thinking about how to really tackle federated learning. But today I want to talk a little bit more about this issue of heterogeneity and how it affects federated learning at various aspects of the machine learning pipeline. In particular, this issue of heterogeneity, that the data and both the data and the systems can vary significantly across the network, makes a really big impact in terms of the optimization methods that we use to train our models in federated settings. So in recent work, we've been looking a lot at trying to answer the question of how does heterogeneity affect federated optimization methods, and in developing new large-scale robust optimization methods that can handle that heterogeneity, both theoretically and empirically. We've also been looking at the issue of modeling. So if the data is very heterogeneous, it might make sense to not learn just one sort of monolithic model for all of that very diverse data, but to try to learn models that are personalized to, say, subsets of the network. So here we've been looking at work in multitask learning and meta learning, and trying to understand those approaches from a principled viewpoint. Okay, and finally, one aspect that I'll talk about in a little bit more detail is that even when you've trained a model, there's a question of how can you evaluate that model and how it performs across very diverse networks. And in particular, there can be major issues with fairness in federated settings. So you might train a model, say, that performs really well on some of the data, but not on other parts of the data. And this can be really critical to think about in federated settings, because you want to make sure there's no sort of situations where there are catastrophic failures of the model that you're learning. All right, so I'm going to talk a little bit about this work in fairness, and some of this work is related to federated learning, and you'll see some of it also extends to a bunch of other applications in machine learning as well. All right, so the potential problem with kind of using federated learning as it's typically applied is that you're traditionally kind of solving an empirical risk minimization objective in the federated setting. Oh. Sorry, am I cutting out?
Yes, you did, but you're back now.
Okay, sorry about that. Should I go back just a slide, or was it earlier than that?
Just one slide.
Okay, cool. All right, let me, sorry, hold on. All right, so yeah, so let's talk a little bit about fairness and federated learning. As a starting point, the way that you typically think about fitting models in the federated setting is solving some empirical risk minimization objective, right? So here, F sub 1, this would correspond to the loss on device 1, F sub 2, the loss on device 2, and so on. And so when solving this empirical risk minimization objective, the potential problem is what you're really trying to optimize for here is the average performance across the network. All right, and the potential issue with this is that while you could do very well on average, there's no accuracy guarantee for individual devices or data points. So it could be that you're doing well on average, but at the cost of performing, say, catastrophically on some of the devices. And more generally, you can do well on average, but with an incredible amount of variation in the performance. And so this is something that we really want to try to limit in order to provide a model that performs well across the entire network. Just to give you one kind of concrete example of this, this is an example with a real federated data set. And what we're doing here is looking at the histogram of the test accuracy across all of the devices. And what you can see is that while this model performs well on average, there are examples where it performs quite poorly, right? And so this is what we want to try to limit when trying to fit a model to this data. Okay, so how can we do this? In this work, we took an interesting perspective, which is that fairness is actually something that's been thought about a lot in other domains. And one domain where they've thought about fairness previously is in wireless sensor networks. There's been work in fair resource allocation, where the resource that they want to allocate there is something like bandwidth over a network. Okay, so we were inspired by this idea, and we thought, okay, what would the resource in machine learning be, right? In this objective, the resource that we're sharing are these loss functions. And the intuition there is that the higher the loss, the more your model is going to be fitting to that specific device or that subset of the data. So drawing inspiration from this prior work, we developed the following objective, which we call Q fair federated learning. And the objective does the following, which is it takes the previous ERM objective and it raises it, each of these losses to an exponent, Q plus 1. So the way you can think about what this is doing is that the larger this value of Q is, the more emphasis you'll be putting on the high losses, right? And in the extreme, this can recover when Q is infinity. This recovers a minimax objective, which intuitively says that you want to minimize the performance on the worst performing device. Okay, but what's nice is that this is a tunable framework. So the intuition is that as you tune Q, you're basically going to be enforcing more uniformity across your distribution. And this is something we've shown both theoretically and empirically. I'll just note quickly in terms of that simple example from before, what we're able to do with this QFFL objective is actually maintain the same average accuracy, but get rid of this catastrophic failure, right? So we're taking the worst performing devices and we're making sure that they perform reasonably well. How do we do that? Well, we're taking a cut from these best performing devices. We're still performing just as well on average, but we're ensuring that you don't have these sort of horrible failures in the system. And this is something that we saw across all of the federated data sets that we've looked at. So this is just a subset. We've looked at this on a bunch of federated problems. And what we find is that on average, we can maintain the exact same mean accuracy, but cut the variance in half. So we can really, not lose anything in terms of average accuracy, but we can really help to enforce fairness in this setting. And I wanted to bring up this problem because we've also generalized this beyond just the problem of federated learning. And in particular, we've developed the following objective, which is a slight variant of what I just showed you for QFFL. And beyond this variant, we've also done something interesting, which is that we take this parameter, which we previously called Q, which is enforcing the amount of fairness, and we're allowing it now to both be positive as well as negative. And I think the intuition for that is best explained in this picture on the left. So at a high level, what's happening with this objective, which we're calling tilted empirical risk minimization, is that these poor performing devices from before, we can think about those as outliers. And so with our previous ERM objective, we were just trying to do well on average. With setting that Q parameter, or here T, to be greater than 0, we're ensuring that we're fitting to those outliers, right? So we're minimizing the worst performance here, the largest distance in linear regression from our line of best fit to any one of those data points. On the other extreme, you could take these outliers and say, I really want to ignore that data. Maybe that data is noise or, corrupted data points, for example. And you can set T to be less than 0 to kind of ignore all of these outliers. So this objective is actually quite general. It's a straightforward modification of ERM, but it has a lot of really nice properties. And so in recent work, we've been looking at this objective for a ton of different applications and also understanding its theoretical behavior. So that was kind of a high-level overview of work both in large-scale machine learning and also this more recent work in machine learning fairness and robustness. I'll end here and just note my research interests broadly are in large-scale machine learning and optimization. I'm also quite interested in machine learning fairness, privacy, and robustness, and problems like meta-learning and multitask learning, which aim to learn with limited data. And today, this year, I'm looking to take 1 to 2 PhD students, as well as hopefully some master's students in my group. Thanks. Sorry I cut out there.